spread out. You want to get, after all your work, take the tightest answer. So which one is going to give us the best answer? That's fully, if you want to just put that as your answer, that's a great answer. But some of you might even come up with a better thing. You might round it to an integer. What's the closest integer to that? Just think integer. What was that? Yeah, but so, and I'm going to put that for my answer. Estimate the instantaneous velocity at t equals 2 seconds. I'll draw here. It's like this guy, because that was the tightest range we had, right? The tightest interval to give us an idea at 1 instant. And I'll just say, okay, so it's roughly about -24, and I'll put the units feet per second. I'll put them here too. When I didn't put the units here, I apologize. So you remember that? It's like sometimes we have to do that if we don't have like a math formula in calculus, and we're just trying to estimate an instantaneous velocity, like the instantaneous velocity of a car at exactly 8:10 p.m. Well, then we can get two periods of time that are as closest together as possible, and we use the average of those two. We just do f of b minus f of a or b minus a. You'll be shocked there. And who's going on beyond Calc 1? So you Calc 2? Anybody going to get a Calc 3? Watch how many times you have to do this in Calc 3. Because you'll have a table. You just have a table values, you go, it says estimate the, and you go, oh yeah, I'll just, and in this gigantic table, you're just going to take the two numbers that are closest together. That's all you'll use. Because you'll be like, that'll give me the closest, the best estimate of what's going on in an instant. Cool. But there is a way to find the answer to this exactly, but we're going to use calculus. We'll get to that later. And some of you are already very curious about that. And that's what we're getting to. So the real idea is what we're getting to is eventually we're going to say, we're trying to find this. This is what instantaneous velocity is. Right, so this tells everyone, here's where math gets cool. You know, what can I calculus? Well, I guess spell it right. Instantaneous velocity then for this problem would be, okay, keep doing your f of b minus f of what? Keep doing that, right? But it's the limit as the difference between b and a approaches 0. So I'm going to put LIM for limit. It's the limit. And I'll just make a little note here and just say, as the difference between b and a approaches what difference? APPROHE. A difference of 0. The difference between the b and the a, that little difference we had there, it was approaching what difference? A difference of 0. Right on top of each other. So this is the word LIM for limit, and that's what we're getting to. So the next section deals with limits. We'll spend the next 3 sections just on limits. It's the what? It's the building block to all of calculus. It's that foundation. We're trying to see what's going on in an instant. So it's the limit, and we'll come up with other notation. We'll write this in different ways. Okay? We can write this a little bit cleaner. Because this looks messy, doesn't it? I want to leave it like this, though. I want to leave it right now. I'll put my quotations right now. That's how I'm going to leave it for now, because that's what we're getting. We get an idea of this, though, right? The average velocity, it's the limit as of this answer, but as which one? As the difference between the b and a got really, really close to a what? 0. We can't say exactly 0 because you can't divide by 0, right? Right now. So we're like, as it approaches 0. As it gets as close as possible to 0. Cool? Awesome. Now, you want to see that graphically? I can show you that graphically. What's this graph look like between 2 and 2.5 seconds? Well, one real quick. What's f of 2.5? And what's f of 2? And thanks for bearing with me on this problem. It's just good to take this problem, look at the graph. And we'll see, what does this look like graphically? F of 2.5 and f of 2. What were these numbers? That was 80 minus 64. I know that's 16, right? Yeah. All right, what's f of 2.5? 0. Is it 0? Yeah. All right. So I'm just going to plot these. At 2.5 seconds, And I'll just put t down here. At 2.5 seconds, it was right here, huh? This being y and this being t. At 2.5 or 0, what was going on at 2 seconds though? How high was it? 4, 5, 6, 7, 8, 9, 10, 11, 12. Go higher. 13, 14, 15, 16. Way up here. Somebody get a dot right here. So right there went at 2 seconds. But this ball was falling fast, huh? This ball went like what? It was going like that. Don't agree? And it's like a curve. And when that graph, is that an upward down parabola or a downward parabola? Downward. You all see that. And it was that portion of the downward parabola, right? And it's just going like this. And that's representing the height. Well, what were we doing, everyone? We kept getting like this. But I heard you say it. Doesn't it just mean slope? Right? So we were getting a slope of what we call, in this case, secants. We started out by getting this slope. That was the first slope. And then when you know what that slope was? That was that first answer to letter A. I think it was negative 32. Do you recall that? But then we took a tighter region. We didn't go all the way from 2 to 2.5 seconds. This time we only went what? 2 to 2.1 seconds? That one you okay if I erase real quick? I didn't know if anybody was copying. So that we got the slope of this. But then we go, well, let's go closer. So then we took, you ready? We took a tighter secant. That's called a secant. When you got a line, it cuts in between the curve. Then we took it from what? 2 to 2.1. So here's 2 right here. And we just went to about here. So now the tangent went like this. But there's still a tiny space between this curve and that tangent line, right? And then we said, let's go even tighter. And we went what? With our little secant line. As this curve went like this. We took it even tighter. And this thing went from here and went to the next point right off the curve. And went like this. So we were getting all these slopes of secants, right? Well, in this box is the slope of the secant. And guess what happens when you finally get the limit as the difference approaches 0 between the difference between B and A of the slope of the secant? You know what we were going to estimate? That estimate we got was the slope of the tangent. Because you're talking about, we're trying to estimate everyone. Here's a curve. Let me get this a little bit better here. That was going like this. And you're trying to get the slope of this curve right here at an instant. And that's called a tangent. Because how many times does a tangent hit a curve? Only once. So we were getting all these slopes of secants. Do you follow me? A secant is some line that cuts to a curve in 2 points. But in the end, we estimated the slope of the what? Of the tangent. Do you follow me? So I want you to all see what it means graphically. We were able to estimate the actual slope of just a tangent. A line that hits the curve in exactly what? One spot like that. And that's calculus. So in this case, this part right here was the slope of all the secants. You add this part to it, and you get a slope of a tangent. You follow? Hey, cool. So welcome to calculus, but now we get to spend, the next 45 minutes doing limits graphically. So in 2.2, let's find limits. But which way? Graphically. And everyone, thanks for your patience on section 2.1. I know you already know about average rate of change of a function, right? But I want you to see where this was going. We were trying to get the tightest region to help us estimate what's the instantaneous velocity. Alright? And we were trying to estimate not the slope of a secant, but the slope of a tangent to a curve. Cool? Alright, and that's calc. That's cool. Calc, well, we estimated it, but eventually we'll write this better. And everyone, you have to agree, isn't this kind of sloppy here, the way I write this? That's not really, elegant. It's not very neat. But we're going somewhere with this. That's my point. We'll clean this up later when we learn some new things, and we can write this really neatly. For limit, we'll just put LIN. But I think we're going to just write something else right here. We'll write something right here between that. Alright. But you gotta admit, this stuff is pretty cool. Calc is cool because everything else was, Just everything was a nice slope of a tangent, of a secant that goes to 2 points in a curve. Now you're getting slopes of tangents. So I'm just going to start out with an image. Alright. Let's just say, you got a graph that went like this. Okay, there's f of x. Oh, and this is the x-axis, this is the y-axis. There's my function f of x. And I'm going to ask some questions. We're going to find some limits graphically of f of x. Someone see this graph okay? I'll get all the chalk off this board so it doesn't interfere with our graph. Hey, does that graph pass the function test? Like in an algebra class? Okay, good. Sometimes I'm going to make sure I didn't draw some goofy graph. I couldn't draw this, right? That's not a function, is it? Good. So this is a function. There's f of x. If you want to put arrows here at the end, you can. Just let that thing keep going up. This x value right here, everyone, is x equal to 2. Yeah, making up off the top of my head. This value right here for y is 1. This value right here for y is negative. And you and I are going to answer these questions. Finding LIM. What's LIM stand for? Limit, yeah. Find a limit as x approaches the value 2 of f of x. Is this right next to it? Say with me. Find the limit as x approaches the value 2 of the function f of x. And I'm going to tell you which side. Alright? So we're going to do it from the left side. So the notation from the left side is, see this 2 right here? In the upper right corner they put a negative. So that means from the left side. You want to even write that in your notes? I think it's good to know that. Now what's that little symbol right there, that little negative off to the top right? It means not to the left, but what? From the left. That way you're communicating to yourself properly, like if you're doing this on a test, you're like, I have to find the limit as x approaches 2 of the function f of x from the left side. So you get your hands or your eyes, a pencil, and you're going to jump on this function on which side of x equal to 2? This side or this side? You're going to jump on this side, aren't you? And you go, what are you going to do? Oh, you're going to take a nice ride. You go, where do you want to get it? You get it on the left side of 2. Well, you can start up here, but we were just talking about this. You might as well get really, really what? Get really close. So how about let's jump on right here. I need you to write it in. What y values are getting closer and closer and closer to? That's the answer. Is that okay with that? Everyone good with that? You're like, yeah, jump on the left side. I could have started here. You're like, well, you don't have to. Just get really, really close to the 2. Write it in. See what y value is approaching. So you just found, like, what's going on. What y value is that getting closer and closer to as you approach that? All right, cool. Not bad. This is limits graphically. Here's my next one. They go quick. This time I put a plus in the top right corner of that 2. Guess what that means? From which side? From the right side, if you want to write that down. So I'm going to need you to hop on this function from the right side of x equal to 2. Over here, you can, but you might as well jump really close. That's what we're talking about. We're going to get really, really close to 2 and write it in. And of course this, we haven't done this before, and there's an open circle there. But remember, the word is approach. That's why calc is cool. I want to know what's it getting close and closer and closer to as you approach 2 from the right side. Let's do it. As I get closer and closer and closer and closer and closer and closer to 2, what y value am I getting closer and closer and closer to? Negative 1. You go, yeah, but at exactly 2 it doesn't exist. Who cares? It's a limit. We don't care what's going on exactly 2. You follow me? Oh, cool. So let's put that answer down. That's a negative 1. Now here's a powerful statement. How about LIM, limit, x approaches 2, and I don't put a plus or a negative up there. That's called a two-sided limit. So, and that's called a two-sided limit. Now it's powerful. The only way you can get a numerical value out of this is that the left side and the right side limits are the same. So that's the only way I can put down a number here. Alright, I can put a number right there. If these two numbers are the same. Well, they're not, so guess what I have to put? Yeah, it does not exist. You wanna write DNE for does not exist? You wanna write non-existent? The two-sided limit does not exist. The only way it could exist, the only way, is if these two numbers what? Are the same. And that would be my answer.
What's the open circle mean?
Great question. Open circles on graphs. We really emphasize it with this open circle. It means there was nothing there. It didn't exist there. Excuse me when I say it, the function's value. So the actual function's value. So at x equal to 2, like this. And I know this is neat because this is a calc question. According to this graph here, what is f of 2? So this is pre-calc. So anyone, I encourage you, that was a great question. Add this to your notes. Pre-calc question. There's the graph. Look at that graph carefully. What is just f of 2? You should be able to find it. And you go, well, there's an open circle there, so I can't use that. Well, where's it filled up? Right there. Cool. By the way, this is interesting. On my first test, Tuesday, students, and we did, next Tuesday. Students don't miss these. This is the one you miss sometimes. You won't miss it. It's like a student misses class. They'll miss the pre-calc question. They'll go and they'll go, it seems like it's broken up here, so I can't put anything. And it's like, no, you gotta look for that dot, right? Awesome. Oh, question, go ahead.
So what if you ask the question without the negative or the positive sign? We have to first of all find the negative, then the positive.
I love it. That's how you gotta think. He goes, you gotta look from both sides.
And see what it's equal to.
That's right. So in everything in this course, if you're looking at something graphically, and they just do something like this, and there's nothing up there from the left, from the right, you're like, well, I'm gonna have to approach them from both sides. I have to think about what's going on both sides. As long as if it's a straight line, no, I'm fine. It's going right through it, so I'm good. But that's how you got to think about it. It's very powerful when they do that. That's very good. That's very good. Hey,